are going to study about thermal expansion. All matter, solids, liquid and gases expand as their temperature increases. The solids and liquids expand slightly on heating, but gases undergo appreciable expansion on heating. From the daily experience, we can say that mercury in a thermometer rises when the thermometer is put in a slightly warm water. And again, when it is taken out of the warm water, the level of the mercury falls down. That means mercury expands on heating. In the case of gases, a balloon partially inflated in a cooled room may expand to full size when it is placed in warm water. Okay, on the other hand, a fully inflated balloon when immersed in cold water would start shrinking due to the contraction of the air inside. So, from all the experience we can say that almost all matter, solid, liquid and gases expand on heating. If you increase the temperature, it expands on heating and it contracts on cooling. So, it is a common experience that most substances expand on heating and contract on cooling. The change in temperature of a body causes change in its dimensions. Dimensions means length, area, its size, volume, etc. So, the phenomenon of increase in dimensions of a body due to increase in its temperature is called thermal expansion. Okay, so if the dimension of the body changes due to increase in its temperature, then the phenomenon is called thermal expansion. Now, we can study the different types of thermal expansion. If the length increases, area increases, volume increases, there are different types of thermal expansion. Hence, the different types of thermal expansion of solids are: number 1, linear expansion; number 2, area expansion or superficial expansion; number 3, volume expansion or cubical expansion. Now, we can study one by one in detail. First, we can study linear expansion. It refers to increase in linear dimensions, for example, length, breadth, height, width, thickness, etc. on heating a solid. Okay, so if a metallic rod is heated, what happens? If its length may increase, its width may increase, its breadth may increase. So, if there is any change in the linear dimensions of the body, then we can say that there is linear expansion. Now, if a metallic rod has length L be the original length of the metallic rod, let the temperature is increased by delta T. For example, if initial temperature is 25 degrees Celsius, now by heating let the temperature increases to 50 degrees Celsius. Okay, so initial temperature is 25 and the temperature increases to 50 degrees Celsius. So, what is the change in temperature? 50 minus 25. Okay, so that is the increase in temperature delta T. Okay, change in temperature is delta T. So, if the metallic rod has length L and the temperature is increased by delta T. Okay, now the length increases by delta L. So, let L be the initial length. If the temperature increases by delta T, what happens to its length? Length increases slightly by delta L. Hence, we can say, experimentally we can say that the increasing length delta L represents the increasing length. Increasing length is directly proportional to the original length, and increasing length is directly proportional to increase in temperature. If temperature increases by a large value, then what happens to its length? Length also increases by a greater value, isn't it? So, increasing length is directly proportional to the original length. Increasing length is directly proportional to increase in temperature. Or we can write increasing length delta L is proportional to L delta T combining, or increasing length delta L equal to, we can change the proportionality by a constant. Here the constant is alpha L into L delta T. Okay, so increasing length is equal to a constant alpha L into L delta T, and the constant alpha L is called coefficient of linear expansion. Clear? So, increasing length delta L is equal to alpha L into L delta T, and alpha L is called coefficient of linear expansion. Okay, and this is a constant for a given material. From this we can write alpha L. What is coefficient linear expansion? Alpha L equal to L delta L divided by L delta T, isn't it? So, hence what is its unit? Delta L. Delta L increasing length, that is meter. SI unit is meter. Here L also SI unit meter. So delta T SI unit is Kelvin, isn't it? So unit of coefficient of linear expansion is, what is the unit of alpha L? Kelvin raised to -1 per Kelvin, Kelvin raised to -1. Now how will you define a coefficient of linear expansion? Let original length is equal to 1 meter, increase in temperature is equal to 1 degree Celsius or 1 Kelvin. So temperature increases by 1 degree Celsius or temperature increases by 1 Kelvin, both are same because the change in temperature 1 degree Celsius and 1 Kelvin are same. Change in temperature, if it is expressed in degrees Celsius and Kelvin, are same. Okay. So let the original length be 1 meter and the increase in temperature let it be 1 degree Celsius or 1 Kelvin. Now how will you write alpha L, coefficient linear expansion, is equal to delta L, isn't it? So how will you define coefficient linear expansion? It is the increasing length if a rod of length 1 meter is increased by how much? 1 degree Celsius or 1 Kelvin. Hence this is the definition. Coefficient linear expansion is defined as the increase in length per unit original length per unit rise in temperature of the solid, and its SI unit is Kelvin raised to -1. Okay children, so this is linear expansion. Now second one, area expansion, or otherwise it is called superficial expansion. Area expansion deals with increase in area. Okay, it refers to increase in area of a material, then that is called area expansion or superficial expansion. Let A represents the original area of the solid. Temperature is increased by delta T. So delta T represents the increase in temperature. Increase in area be delta A. Same as before, we can write increase in area is directly proportional to original area. Okay. It is also directly proportional to increase in temperature. Increase in temperature, let it be delta T. Okay, delta T. So increase in area depends on the original area and increase in temperature. Or we can write increase in area is equal to, here a constant. Here the constant is coefficient of area expansion. Therefore, we can write alpha A. Coefficient of area expansion into A delta T, and this alpha A is called coefficient of area expansion, or otherwise called coefficient of superficial expansion. Okay children. So coefficient of area expansion is alpha A, and delta A is equal to alpha A delta T. Here also how will you define alpha A? We can write alpha A is equal to delta A divided by A delta T, isn't it? So if A is equal to, initial area is 1 meter square, temperature increase is 1 degree Celsius or 1 Kelvin. Now how will you write alpha A? Alpha A equals delta A. So how will you define coefficient of area expansion? It is the increase in area of a solid if its original area is 1 meter square and if the temperature is increased by 1 degree Celsius or 1 Kelvin. So if the temperature increases by 1 degree Celsius or 1 Kelvin and if the initial area is 1 meter square, now the coefficient of area expansion will always be equal to increase in area. Hence coefficient of area expansion is defined as the increase in area per unit original area per unit rise in temperature. Clear? Now what is the unit of coefficient of area expansion? Same as coefficient of area, linear expansion, its SI unit is delta A meter square. Here also A meter square, that cancelled, and the coefficient of area expansion, its SI unit is Kelvin raised to -1. Okay children. Third one, we can study volume or cubical expansion. Expansion in volume due to increase in its temperature is called volume expansion. Let V be the original volume, delta T be the increase in temperature, and delta V be the increase in volume. Same as before, we can write increase in volume. It depends on what all factor? It depends on original volume. It also depends on increase in temperature, isn't it? So delta V equal to V delta T, or delta V equals a constant. Here the constant is alpha V into V delta T. Clear? So alpha V is a constant and that constant is called coefficient of volume expansion or cubical expansion. Clear? So here the constant is alpha V, which is called coefficient of volume expansion, and its SI unit is same, Kelvin raised to minus 1, because alpha V equal to delta V divided by V delta T, no? So its unit is Kelvin raised to minus 1. Now how will you define alpha V? Alpha V equal to delta V divided by V delta T. If delta V by V, that is the fractional increase in volume. Okay, delta V by V is the fractional increase in volume. Now, how will you define coefficient of volume expansion? We know alpha V equal to delta V by V delta T. It can be defined in another way also. Delta V by V equal to alpha V into delta T, isn't it? Alpha V into delta T. If delta T equal to 1 degree Celsius or 1 Kelvin, now how will you write alpha V? Alpha V is equal to delta V by V, isn't it? So, coefficient of volume expansion can be defined as the fractional increase in volume per unit degree or per unit rise in temperature. So, coefficient of volume expansion is defined as the fractional increase in volume per unit rise in temperature. So, alpha V is the fractional increase in volume per unit rise in temperature. Okay? Now, we can derive the relation between coefficient of linear expansion, coefficient of area expansion and coefficient of volume expansion. For that, consider a solid cube of side L. Let the cube be heated to raise the temperature by delta T. Okay, let the cube is heated so that the temperature increases by delta T. And consequently, its each side increases by delta L. Now, before heating, length of each side is equal to L. Area of each face is equal to L square. What is the volume of the cube? L cube. After heating, what happens to its length? Length increases by delta L, isn't it? So, what is the length of each face now? L plus delta L, because if the temperature increases by delta T, we know the length increases by delta L. So, what is the length of each side? L plus delta L. What is the area of each face? Area of each face is L plus delta L the whole square. Clear? What is the volume of the cube now after heating? Volume of the cube is L plus delta L the whole cube. Clear? First, we can derive the relation between coefficient of linear expansion and coefficient of area expansion, alpha L and alpha A. Now, we can write delta A. Delta A represents the increase in area. We know that if temperature is increased, what happens to its length? The length increases, area increases, volume also increases. So, increase in area can be written as final area minus initial area, isn't it? What is the final area? Final area after heating, its area becomes L plus delta L the whole square. That is the final after heating, minus what is the initial area? Initial area is L square. Clear? So, we can simplify it. L plus delta L the whole square can be written as L square plus 2L delta L plus delta L square minus L square. Clear? So, this is L square and L square get cancelled is equal to 2L delta L. Here, delta L square can be neglected because delta L, the value of delta L is very small, of the order of millimeter or less than millimeter, very small value. So, if a metallic rod is heated, its length increases by a very minutely small value. So, delta L is very small and hence delta L square is negligibly small and hence it can be neglected. Clear? So, delta L square is negligibly small. Negligibly small and hence that value can be neglected. So, what is the increase in area now? Increase in area delta A equal to 2L into delta L. So, delta L square is neglected. So, we can write delta A equals 2L into, what is this delta L? We know that increase in length delta L is equal to alpha L into L delta T. Okay children. So, substituting the value of alpha L here, delta L here, what is that? Alpha L into L delta T. Substituting the value of delta L as alpha L into L delta T, we can substitute. So, how will you write increase in area delta A equal to 2L square alpha L into delta T. Okay, 2L square alpha L into delta T. What is this L square? L square is the initial area which is A. So, delta A equal to 2A alpha L into delta T. Here A and delta T can be taken to the other side. So we can write delta A divided by A delta T is equal to 2 alpha L. But what is this delta A divided by A delta T? Delta A divided by A delta T is, we know it is alpha A, coefficient of area expansion, isn't it? So alpha A equal to 2 into alpha A. So the relation between coefficient of area expansion and coefficient of linear expansion is alpha A equal to 2 times coefficient of linear expansion, that is alpha A. Okay children? Now we can derive the relation between alpha L and alpha V, coefficient of linear expansion and coefficient of volume expansion. First we can write increase in volume delta V. Delta V is the increase in volume. Delta V equal to, we know it is final volume minus initial volume. What is the final volume after heating? It is L plus delta L the whole cube minus the initial volume before heating is L cube. Okay, is equal to L plus delta L the whole cube can be written as L cube plus 3L square delta L plus 3L delta L square plus delta L cube minus L cube. Clear children? Here L cube and L cube get cancelled and remaining we can write 3L square delta L plus 3L delta L square plus delta L cube. Here delta, we know that delta L, the increase in length, it is very small, mildly small, and hence delta L square is also very small. Delta L cube also equally very small. So hence we can neglect the terms containing delta L square and delta L cube because they are negligibly small. So here 3L delta L square and delta L cube can be neglected because they are negligibly small. Clear children? So delta V can be written as increase in volume, delta V can be written as, these two terms can be neglected. So remaining we can write delta V equal to 3L square delta L is equal to 3L square into, we know what is this delta L, coefficient of linear expansion. Relating coefficient of linear expansion, we can write delta L is equal to alpha L into L delta T. Substituting for delta L, we can write alpha L into L delta T. Here is equal to 3L square into L cube, 3L cube alpha L into delta T. Or we can write delta V equal to, what is this L cube? That is the initial volume. Before heating, the initial volume is L cube. So we can write 3V alpha L into delta T. V delta T can be taken to the left hand side. We can write delta V divided by V delta T is equal to 3 alpha L. What is this delta V divided by V delta T called? That is coefficient of volume expansion. So alpha V equal to 3 alpha L. So the relation between coefficient of volume expansion and coefficient of linear expansion is alpha V equal to 3 alpha L. Clear? So the relation between area expansion and linear expansion is alpha A equal to 2 alpha L and volume and linear expansion is alpha V equal to 3 alpha L. Now we can do some numericals relating thermal expansion. First question, the length of metallic rod at 30 degrees Celsius is 2 meter. It is heated uniformly till its length increases by 1%. Find its final temperature. Coefficient of linear expansion is 25 into 10 raised to minus 6 per degree Celsius. So length of the metal rod. So what are the values given? Original length is equal to 2 meter. Okay. Length of the metal rod at 30 degrees Celsius. So initial temperature is 30 degrees Celsius. Initial length is 2 meter. It is heated uniformly till its length increases by 1%. So what is the increasing length? Increasing length is equal to 1%. 1% of original length. Okay, length increases by 1% means delta L is 1% of original length. Is equal to, we can write 1% means 1 by 100. 1 by 100 of original length, which is L. That is also given. We have to find out the final temperature. So initial temperature is T. We know that change in temperature is delta T. So what is the final temperature? We know final temperature is equal to, what is the final temperature? T plus delta T, because delta T is the increase in temperature. Whenever a metal rod is heated, we know that length increases, temperature increases, length also increases. So increase in temperature is delta T. So what is the final temperature? T plus delta T. So this T plus delta T we have to calculate. Here coefficient of linear expansion alpha L is also given, 25 into 10 raised to minus 6 per degree Celsius raised to minus 1. So these are the values given. Original length is 2 meter, original temperature is 30 degrees Celsius, increase in length is 1% of the original length, final temperature we have to find out, alpha L is also given. We have the direct relation. What is the formula for coefficient of linear expansion? We have alpha L is equal to delta L divided by L into delta T. Clear? What is this delta L by L given? Delta L by L. Delta L by L is equal to 1 by 100. Clear? So delta L by L is given as 1 by 100. Delta T we have to find out is equal to alpha L is also given, 25 into 10 raised to minus 6. Clear children? So delta L by L, that is a fractional increase in length, that is 1%, that is 1 by 100. And delta T we have to find out, and simplifying, delta T is equal to 1 by 100 into 25 into 10 raised to minus 6. After simplification, we get the answer as 400 degrees Celsius. So delta T, increase in temperature, the change in temperature is 400 degrees Celsius. What is the initial temperature? 30. What is the change in temperature? 400. So what is the final temperature? Final temperature is T plus delta T, that is 400 plus 30, that is equal to 430 degrees Celsius. Clear? So the increase in temperature is, or final temperature is T plus delta T, which is 430 degrees Celsius. Now second question, the coefficient of volume expansion of glycerin is 49 into 10 raised to minus 5 per degree Celsius. Find the fractional change in its density for 30 degrees Celsius rise in temperature. Fractional change in density we have to find out. Okay. So what is the change in temperature given? Delta T is equal to 30 degrees Celsius. Rise in temperature. What is the coefficient of volume expansion? Alpha V equal to 49 into 10 raised to minus 5 per degree Celsius. These are the two values given. We have to find out the fractional change in its density. First we can find out the fractional change in volume. Fractional change in volume is delta V by V. We know delta V by V equal to alpha V into delta T, isn't it? Alpha V equal to, what is alpha V? Delta V divided by V into delta T. So here we can write delta V by V equal to alpha V into delta T. Here delta V by V we have to calculate. So delta V by V, that is a fractional change in volume. Alpha V, what is alpha V? 49 into 10 raised to minus 5. What is the increase in temperature? 30. So after simplification you will get 1.47 into 10 raised to minus 2. No unit, because delta V by V both are your volume, no? So fractional change, hence delta V by V is 1.47 into 10 raised to minus 2. Here this is the fractional change in volume. Here we have to find out the fractional change in density. Here density is equal to mass by volume. Here as the mass remains constant, the fractional change in density is equal to the fractional change in volume. Okay, so fractional change in density, fractional change in density, fractional change in density is equal to fractional change in volume, because mass remains same, constant. So fractional change in density is 1.47 into 10 raised to minus 2. Okay children. A blacksmith fixes iron ring on the rim of a wooden wheel of wood cart. The diameter of the rim and the iron ring are 5.243 and 5.231 meter at 27 degrees Celsius. To what temperature should the ring be heated so as to fix the rim of the wheel? Okay, so here this is a wheel, it is a wooden wheel, and here this represents the ring. This represents the ring. Okay. And what is the diameter of the ring? Diameter of the ring is equal to 5.231. So diameter of the ring is 5.231 and the diameter of the rim of the wooden wheel is 5.243. In order to fix the ring to the rim of the wooden wheel, it should be heated. The blacksmith does the heating process. So if it is heated, what happens? This iron ring expands and tightly fixed with the rim of the wooden wheel. Okay, so that is the process. Here in the question, coefficient linear expansion is given. For iron, it is 1.2 into 10 raised to minus 5 per degree Celsius. Here, the initial diameter of the iron ring, this is the ring. Initial diameter of the iron ring is 5.231. What happens when it is heated? This iron ring, if it is heated, it expands and it tightly fixes the rim of the wooden wheel. Okay, so that is the process of tightening the wheels of the bullock cart. If the ring is heated, it expands and it tightly fixed with the wooden wheel. So initial diameter of the ring is 5.231 meter. And what happens if it is heated? It expands, it tightly fixes the rim of the wooden wheel. So what is the increasing length? Final minus initial, isn't it? 5.243 minus 5.231. Then what is the initial temperature? Initial temperature is 27 degrees Celsius. We have to find out to what temperature should the ring be heated so as to fix the rim of the wheel. So we have to find out the final temperature. Final temperature is T plus delta T. First we can find out the increasing temperature using the direct relation. We have the relation increasing length. Increasing length delta L is equal to alpha L into L delta T. Clear children? Delta L, what is the increase in length? 5.243, 5.243 minus 5.231 is equal to alpha L, that is given 1.2 into 10 raised to minus 5. Original length represents 5.231, 5.231 into delta T. Okay, so using this formula, using the simplification, we can find out delta T. After simplification, we will get delta T. The increase in temperature delta T equal to 191.2 degree Celsius. This is the value of increase in temperature. Then we have to find out the final temperature, isn't it? T plus delta T. T plus delta T is 191.2 plus what is the initial temperature? 27. So after simplification, we get 218.2 degree Celsius. Okay children, so final temperature is 218.2 degree Celsius.